Welcome to the last or third lecture for week 10. We're going to continue with lighting considerations, and now we're going to talk about fluorescent lighting. First of all, we had covered incandescent lighting, which is real simple. Send a lot of current through a high resistive wire and heat it up to the point that it gives off light. Very simple, incandescent. Fluorescent lighting is a little more complicated. It typically is a two-step process. The first step is we need to produce an ultraviolet radiation. The step two is we need to produce a visible light. So it's typically a two-step process. So step one in a typical fluorescent lamp is I create an arc. More complicated fluorescent lights, which we're going to talk about later, actually I can use a real high electromagnetic field, but we'll talk about that later. Most fluorescent lamps create an arc. This arc, which is created on the inside of an enclosed tube, this tube is filled with a little bit of mercury under a vacuum, and that mercury under a vacuum turns into a vapor. And when I pass an arc through that mercury vapor, it excites the mercury vapor and it gives off ultraviolet radiation. Ultraviolet radiation. So that's a short wavelength electromagnetic wave outside of our visual spectrum. So we can't see that first part. Now, that's why we have to have a second part. Inside the fluorescent lamp is a coating. It's coated with various types of chemicals called phosphors. When these phosphors are hit with an ultraviolet radiation, they get excited, and when the electrons fall back to their normal state, they give off a visible light. So fluorescent lamps are a two-step process. I have to excite the mercury vapor to the point that it gives off ultraviolet radiation, either with an arc or a high electromagnetic field, and then that ultraviolet radiation has to strike another chemical that will give off light, visible light, called phosphors. Now, all fluorescent lamps require a ballast. A ballast does two things for the fluorescent light. It increases the voltage. In other words, it steps up the voltage just like a transformer does. That's so I can strike an arc to create an arc. So it increases the voltage. And then once I have an arc, think like welding, once I have an arc going, I have to be able to regulate the current flow. So the ballast increases the voltage and it regulates the current flow. Now, older ballasts in particular, impacted power factor because they're a magnetic coil, like any other transformer. The amount of impact that the ballast has on the power used by the fluorescent lamp is called the ballast factor or allowance factor. And some ballasts actually add to the amount of energy used by the overall lamp, and some ballasts actually make the lamp work a little more efficient and lower the energy used by the lamp. Now, there's three types of ballasts out there. The older version, or the oldest version, is known as a magnetic ballast. They were an inductive load, which after you went through the utility billing, an inductive load has an adverse impact on power factor. And the old magnetic ballast could add up to 25% to the wattages of the fixture, or all the lamps. So, not good. After that, they came up with a hybrid ballast. It wasn't out very long. I managed to live through it. It had less impact on power factor and added less wattage to the fixture. So it was an improvement. Well, nowadays we have electronic ballasts. They're the most common type of ballast out there right now. They have no impact on the power factor, and in some cases, the ballast factor itself is less than 1, that makes the power consumption of the lamps more efficient. So you can actually have a ballast factor of 0.98. Here's an example of some ballast factors. This happens to be compact fluorescence up here. Here are some fluorescent fixtures. If we take, for instance, a single lamp 24-inch T8 fixture that's got a magnetic ballast, if we slide all the way over, it's got a ballast factor of 1.41. So this ballast actually adds 41% more energy usage than the lamps itself use. So that's significant. Up here, this compact fluorescent, a one twin 5-watt lamp, low wattage, but using a magnetic ballast, has a 1.8 allowance factor. So the lamp's only 5, but it uses a total of 9 watts because of the high ballast factor. So again, ballast factor adds the amount of energy used by the lamps, or the total lamps in the fixture. Fluorescent lamp types have different categories. There's simple fluorescent lamps, like we know, the long tubes, or tubes bent in a U shape, or tubes bent in a circle. They're known as simple fluorescent lamps. Then we have compact fluorescent lamps, the ones that were supposed to be used to replace incandescent lamps. We have a special category called inductive lamps. Those are ones where they replace the arc on the step 1 of light production with a magnetic coil. That high magnetic field actually excites the mercury inside the lamp to give off the ultraviolet radiation. So those are called inductive lamps, but they're still a type of fluorescent. And then finally, a specialized category of fluorescent lamps called high intensity discharge, HID. These include mercury vapor lamps, metal halide lamps, high pressure sodium lamps, and low pressure sodium. So there's 4 types of high intensity discharge lamps. What do all these lamps have in common? They all contain mercury. They all give off ultraviolet radiation. The ultraviolet radiation inside these all stimulate some sort of chemical to give off a visible light. So in simple fluorescent lamps, we have a higher efficacy, in other words, more lumens per watt than incandescent lamps, which isn't saying much. They have a longer lifespan, incandescent lamps, by roughly a factor of 5 to 10, so about 10,000 hours. They are extraordinarily expensive to dim. In fact, in my lifespan, I have never seen a fluorescent lighting system dimmed. So compared to incandescents, fluorescents are very expensive to dim. They have more expensive fixture, more expensive lamps than incandescent. There's a cost associated to disposing them because they're a hazardous waste because of the mercury. You typically only can get color rendition up to about 80 compared to incandescents, which are 90 to 100. The older magnetic ballast adversely impacted power factor and added energy usage to the fixture. The ballast was one more component that can fail, so the more components, the more the light can fail. Older standard fluorescents were harder to fit into the building architecture because of their shape. They are impacted by the environment. They're temperature sensitive. I don't know if anybody out there has tried firing up a fluorescent lamp in the cold. An older fluorescent that wasn't meant to be in a colder temperature, they don't do well. The colder the temperature, all the way down to the point where they don't fire at all. The ends glow and that's about it. Next we have compact fluorescence. Basically same conditions as simple fluorescence, so you can apply all the conditions from a simple fluorescent to compact fluorescence. The only difference is these lamps are more architecturally friendly. In other words, you can fit them in more situations. You can screw them in where you used to put in standard incandescents. Induction lamps, these are the specialty lamps. Basically, they took a fluorescent lamp, they took the arc out of either end, and then they wrapped wire around the tube, and then a strong current applies, causing a real strong magnetic field. This magnetic field excites the mercury vapor inside the tube, gives off the ultraviolet radiation, and just like other fluorescents, that ultraviolet radiation stimulates a chemical, phosphor, to give off visible light. Now, the loss of the arc actually helped the tube increase the lamp life. So believe it or not, inductive lamps have some of the longest lifespan of any of the lamp types we have out there. So a typical inductive lamp can live for over 100,000 hours. But they have a huge negative. The biggest negative is that high magnetic field produced to excite the lamp is disruptive to other electromagnetic signals in the building, like cell phone, all the networking in the building. So consequently, in this modern day and age with everything that's wireless and everything we're doing otherwise, these strong electromagnetic fields are not welcome. So inductive lamps, even though they have really long lifespan, are not in wide use. Then we have HID lamps, high intensity discharge lamps. This is a fluorescent lamp that was reduced down basically to the size of your finger. It's now called an arc tube instead of a fluorescent lamp. Now what they did is to get more light out of it, the arc jumps across the whole tube and not just the ends, and they run more voltage, so it's got a little beefier ballast in it. Now the reason they came up with HID lamps is to try to fit the architecture of a building better and use fluorescent lighting like in high bay areas. Now, this little arc tube is filled with various chemicals to get different effects. It's still a fluorescent light at heart, and again, they're used in high bay areas and outside lighting, so they're more tolerant of temperature differences. There's only 4 different types of HID lamps: mercury vapor, metal halide, high pressure, and low pressure sodiums. Now, the bad part about these lamps, they all have a problem with something called strike-restrike time. This strike-restrike time means that when the lamp is first turned on, that arc tube has to warm up before it actually creates light. So there's a warm-up period. It can be as high as 5, 6, 7 minutes. The other problem is when you turn these lights off, they typically have to cool down first before they restrike. So that's called the restrike time. So in total, some of these lights, once you have them on and turn them off and try to turn them back on, there could be a 15-minute total turnaround time to get these lights back on. That can be a security issue. It's definitely an inconvenience. So consequently, these lights were put in areas where once you turn them on, you leave them on. All these lamps have a problem with depreciation prior to lamp burnout. So these lamps lose a lot of their lumen output at the latter part of their life prior to the lamp actually going to a complete failure. So their efficacy has a severe drop-off in their last year of life. So their energy use goes way up considering the light output. We talked about the strike-restrike time already. Again, this is a safety issue. Stores take this into consideration when they put these types of lightings in. Lamp depreciation, fluorescent lamps, all fluorescent lamps are prone to, that should be lamp depreciation, not damp depreciation. This is a decrease in lumen output, in some cases can be significant. We talked about that. The lamp or lumen output depreciation actually happens before the lamp itself burns out. So most manufacturers recommend relamping prior to lamp burnout to increase the lamp's efficiency. So if we look, this one is metal halide, one of the HID lamps. It's the one most in common use. Metal halide is used because it has the best color rendition. So you see it used in a lot of high bay areas, box stores, etc. Metal halide is used outside because, again, out of the 4 types of HID lamps, it has the best color rendition. So pros, excellent color rendition, gives off a white light. On the con side, it's only medium efficacy, 69 to 100. Can be position sensitive, but you don't see those much anymore. They have a slightly shorter lifespan than some of the other HID lamps at 15,000 to 20,000 hours. They still contain mercury. They give off an awful lot of radiation at the arc tube, and their strike-restrike time can be up to 15 minutes. High-pressure sodium lamp, you can see the distinctive yellow color. The high-pressure sodium has a lot higher efficacy if you compare it to the metal halide, all the way up to 150 lumens per watt. That's extraordinarily high. They have quite a long lifespan at 24,000 hours. They're not position sensitive, they're not voltage sensitive, but on the con side, they have poor color rendition. They have a color rendition index down in the 20s, so not real good at distinguishing color. And they still have a strike-restrike time, a little better than metal halide, but it's still 5 to 8 minutes. Now, here's a comparison on the left of a high-pressure sodium, the same parking lot with metal halide. You can see the difference in what color rendition makes. Now, if you filled this parking lot, both parking lots, with different colored cars, the people in the high-pressure sodium parking lot would have a harder time distinguishing colors. Metal halide, no problem. And then finally, low-pressure sodium. You're going to be really hard-pressed to find one of these lamps in operation. They give off a really, really deep orange color. Ugly, jaundice. On the Pro, they have the highest efficiency of any lamp out there. They have an efficacy of up to 200. They also have a long life, greater than 24,000 hours. But here's the rub on the con side. Low pressure sodium has the worst color rendition index of any light source. It has a color rendition index of 0. In other words, you can't distinguish any color whatsoever under this light. Everything looks the same. Now, if you were to look at this same picture during the daylight, this is a red brick building with white facing, white window trim, but fire engine red brick. Everything looks roughly the same. Color rendition index 0. This ends lecture 10C. You now can proceed to assessment 10. Thank you.